So let's take a look at this function r of x equals x squared plus 2x over x squared plus 3x plus 2. First thing is first, we'll find the domain. Now remember, when you find the domain, you have to factor your numerator and denominator. So numerator, I can factor out a GCF of x. Denominator, let's see what I get when I factor out that. Looks like x plus 1 and x plus 2. Now, before you reduce out the x plus 2's, I see that that is in common. We have to make sure you judge your domain first, so don't reduce it yet. We're going to figure out what will make this denominator equal to 0, because we are not allowed to divide by 0. So the domain has two different restrictions. X can't equal to -1, and x can't equal to -2. So I'm going to write both of those restrictions down because that is the only thing that we have to use our original equation for. Everything else we can use the reduced equation. So that's why domain always goes first, and then you will use the reduced anytime after. So this is a time now that I can reduce out the x plus 2's because I noticed that that is a common factor. So my reduced form of my r of x is going to be x over x plus 1. Now technically this isn't what r of x equals. This is the reduced form of r of x. So our graph very much so mimics what x over x plus 1 looks like. It just has a few little differences that we're going to talk about. So after we figure out our reduced form of our equation, then we're going to talk about whether or not this equation has any holes. Now because we had canceled out a factor, that's x plus 2, that means there's going to be a hole at, and then let's figure out where the coordinates are. Remember, you should always have an x and a y when you're trying to figure out the coordinates of the hole. So I'm going to first figure out the x by setting the factor we had canceled out equal to 0. Right, so my x value is -2. If you recall, I'm going to put in -2 into the reduced form, not our original one up there, because if you put it in this original one, it's going to give you something in the bottom that you don't want. So I didn't mean to really cross this out. I just want you to know we're not going to use the original equation to find out what the coordinates of the hole is. So I'm going to substitute in here -2 over -2 plus 1. Looks like I'm going to get a +2. So if I were to go back, it looks like my hole is at -2, 2. That means when you're graphing your equation, you know, it's going to look like a normal equation, and then suddenly it's going to have an open dot there. But it's kind of helpful because you actually have a dot there to connect to. You'll see what I mean in a little bit when we actually start graphing it. Our next one is to find the y-intercept. Recall that's when you put in 0 for your x. I'm going to use my reduced equation again because it's going to be easier for me. If I put in 0, I'm going to get 0 over 0 plus 1, which is 0 over 1. It's okay to have 0 in the numerator, which means I have a y-intercept at 0, 0. You'll also notice that this happens to be an x-intercept as well, but I'll kind of show you what that looks like when you're solving for the x-intercept, which I believe is our step number 5. To find our x-intercepts, you're going to set the y value equal to 0, or in this case, r of x equal to 0. So we'll say, oh, when does 0 equals x over x plus 1? Again, if you want to take the shortcut, you can take the numerator and just set it equal to 0, or you can solve this the legitimate way, and you can kind of see that that's shortcut's going to work out for us. So I'm going to cancel out my x plus 1's after I multiply it on both sides. It reduces to be 1 times x on the right-hand side, aka x. On the left-hand side, you get 0 from multiplying 0 and x plus 1. So I happen to have the x coordinate to be at 0. So that's why my x-intercept is also 0, 0, because the origin happens to be both an x-intercept and a y-intercept. For step number 6, that's us finding our asymptotes. So the very first thing I'm going to find for my asymptotes are the vertical ones. Now remember, we have to use the lowest term, so we're going to use this equation here and set our denominator x plus 1 equal to 0. When I solve that, x equals -1, that is my only vertical asymptote, not at x equals -2, because our hole actually happens there. So you shouldn't have a vertical asymptote where a hole is. Super important. Next line of business. So I dealt with this branch. Now I'm going to go looking over here. So either you'll have a horizontal or an oblique asymptote. We just don't know which one yet until we look at the degree of my numerator and the degree of my denominator. So if you're looking at my numerator here, the degree of this numerator is 1. This degree of the denominator also happens to be 1. So these happen to be the same number now, which means I'm not looking at this branch here, where the degree of the numerator is smaller than the degree of the denominator. And I'm not looking at this one either, where the degree of the numerator is bigger than the degree of the denominator. I'm looking at this middle branch. So the degrees of the numerator and denominator are the same. That tells me I have a horizontal asymptote. My horizontal asymptote is at y equals leading coefficient of the numerator over leading coefficient of the denominator. So I got to go back to my reduced function. Notice the leading coefficient of my numerator is 1, so I'll write that. And the leading coefficient of my denominator is also equal to 1. So if I do 1 divided by 1, my horizontal asymptote is at y equals 1. So it's different than the other ones because we have our horizontal asymptote not on the x-axis. Very last step is to figure out if I have any cross points. So I am going to set up my system here to figure out, will this graph ever cross my horizontal asymptote? So I'm going to use my answer from my last one to figure out, will I ever have them cross with each other? So my reduced version of my function is x over x plus 1. I'm trying to see if these ones will ever intersect. So both of them equal to y according to the rules of substitution. That means I can set them equal to each other. So x over x plus 1 equals 1. So let's go ahead and solve this and see if something comes out. So if I multiply both sides by x plus 1, on the left-hand side, the x plus 1s will reduce out to be 1, right? And then I'll have x left over on the left. On the right-hand side, I have 1 times x plus 1, which really is just x plus 1. So if I continue to solve, I can subtract x on both sides. You'll notice it turns into 0 equals 0 plus 1, which is saying 0 equals 1. This is not a true statement. So because this is not a true statement, that means I have no cross points for this problem. And this is all the information. Eventually, we're going to graph all of it onto one single grid.